now is from Shortlist 2020 Combinatoric 1 problem. And this asks about the permutations of 1 through n. Permutation. I'm sorry, I'm not writing the verbal formulation of this, but I'm just telling you what the problem is. Permutation. A1, A2, AN. The thing is, find the number of permutations which satisfies the conditions, these inequalities. Okay. So find the number of
I think there's something wrong with the screen.
okay. What is wrong exactly? I will try to fix it.
It's shown that it's not shown to me here.
You cannot see external meeting participants cannot access this way after the meeting. Right. So you cannot see anything on the whiteboard?
No, it shows me the screen that preparing your whiteboard experience.
It's working for me.
Preparing your whiteboard experience. Okay.
If it doesn't work, one thing you can try is leaving the meeting and then exiting the meeting and then rejoining. It might fix it.
So for Abdullah and Adham, you can see?
Yeah, it's fine.
Yeah, it's fine for me too.
Okay, maybe Karam. Okay, how is it now, Kalam? Is there a difference?
Now it works. Thank you.
Okay. So is the problem clear?
Yeah.
Yeah, it is clear.
Yeah, finding the number of these permutations with these inequalities. Okay, what is the first thing that you would do? As soon as you look at the problem, what's the first thing that you would do?
I would try a few examples.
Yes, exactly. This is the first thing you should do. You should look at, starting with even n equals 1, which is a trivial situation. N equals 1, n equals 2, n equals 3, n equals 4. It's getting exponentially, maybe more than exponentially, more difficult already but it's just, with n equals 4, there are just 24 permutations, and you will write them down and check the inequalities. Find maybe you are smarter, you will not have to write 24 permutations, right? You will see, obviously, for example, some situations are not possible. You will cross them easily. You will find the answer. Maybe for n equals 5 as well, you will find the answer like this. And try to on the one hand, you will try to understand how the number depends on n, how the number of permutations. So it will form a sequence, right? The number of permutations for n equals 1, the number of permutations for n equals 2, for n equals 3. It will form a sequence. One thing, would you see a pattern in the sequence? This is one thing you should have in mind. And the second thing, it's not just the number of permutations, but when you actually write the permutations that satisfy the condition, do you see a pattern in the permutations themselves? Do you see a structure which is hidden in these inequalities? But when you write down the permutation, somehow you see, okay, much more, another structure might appear. These are the two questions that you must have in mind when you look at the small cases. So this is what I'm going to write. First, we check. Yeah. First, we check small values of n. Two thoughts in mind. One is the number of permutations, the answer. As a sequence in n. Do we see a pattern? The answer is the number of permutations, right? This is what I mean. Because the question asks about the number of permutations. This number might itself, this number might have a formula in n and might have a pattern, but maybe more importantly than the number is the permutations which satisfy the condition. Do we see a structure in those permutations? By structure, it's really what I mean is really just, any kind of information about these permutations, which is just not obvious from this, okay? But when you write down those, for example, for n equals 5, if you find the permutations that satisfy this, you might see, a pattern which is common to all of them, that is just not obvious from the inequalities that we don't see right now. After writing them, you can see, do we see a pattern structure in those permutations? Probably the first thing here is exactly what you thought when you said you would try a few examples. Right? You said you would try a few examples. You would look at small values of n. The first thing you probably thought is, okay, I will try to find the number of permutations and see how it depends on n, how it increases with n. The another thing is, even though it actually just asks about the number of permutations, well, the number of certain objects which satisfy a certain property. So before counting them, we really want to understand the objects themselves better. Counting is sort of the second stage. This is a counting problem, but in all counting problems, this is the thing, really. Before counting, there is more understanding. Okay, with this, I let you think on this for maybe, let's say, at least 10 minutes. And then I'll ask you. Okay, Karim has just joined, right? So Karim, can you also introduce yourself? I actually introduced myself before Kerem and Karim has come, so I can repeat the introduction of myself. My name is Melih Üçer, as you can see. I am a former IMO medalist from Turkey, and right now I am a mathematician, postdoctoral researcher in Saudi Arabia, King Abdullah University of Science and Technology. Karim, where are you from? Can you hear us?
Yes.
Yeah, which city are you from?
Nablus.
Nablus, okay, like Abdullah. Okay. Nice to meet you.
Nice to meet you too.
I will send the whiteboard to Hassan. He's online, alhamdulillah. Page one. Okay, I should ask now, what have you calculated?
I
So far,
finished the problem.
what?
I finished the problem.
Oh, you already finished? Oh,
Mm.
okay. Okay, well, I will then write the other problem, N1 on the next board, but come back to this. So it's early to, well, what you can do is you can send your solution to me on WhatsApp, because if you explain it here, it will spoil. The other students can still think. You can send your solution to me on WhatsApp,
Okay.
but and then okay, then I'll text you the other next problem. For this one, others, what have you found?
I think I have an observation, but I'm not sure. I think if we have a solution, then we want to construct another one. We do that by swapping two numbers of the permutation. I think that swap must be at most one step.
So in the whole permutation, you mean to obtain this from this one?
Yeah,
Only this one?
I want to obtain a new permutation from a valid one, a previous valid one.
With one swap? Well,
Yeah,
yes, but which do you mean swap of just any two numbers?
two numbers.
But with this you can produce all the permutations with one swap and then another swap, another swap.
I didn't understand.
Maybe I didn't understand you correctly. So let's discuss this here. I'll- So can you explain with the specific numbers examples, like for example n equals 4? What do you mean?
Like for n equal 4, if we have a1 and a2 and a3, a4 permutation, which is a valid solution. Then we swap. We want to get another one.
So if
If
this
we
is a
swap,
solution,
swap,
then for example you are saying if I swap, for example, these two, a2, a1, a3, a4 is also a solution? Or
actually, I'm not sure.
yeah. No, because this is too flexible. If you say always, you can swap the two numbers, then by swapping this and then swapping again and swapping again, you can reach all the permutations. There has to be some well, in general, by the way, this is good information about the permutations. This is really good information. So this is not trivial. So any permutation at the end can just be obtained by one swap, finite number of swaps. All permutations can be decomposed into this. Well, in fact, it's not even hard to prove once you understand that this is the case. Because, so I will not write the statement like this because this would imply that all permutations would be in there. But maybe what you can tell us is what prompted you to make this observation, because sometimes I know from students they actually see something, they have an intuition, but they don't find exactly the right way to formulate that intuition. Your intuition definitely comes from an observation. Tell us the observation itself, and then we can try to help you formulate it better.
Actually, my observation was if you consider the permutation 1 up to n, 1, 2, 3 up to n, then
Yeah.
we swap any two consecutive numbers, the resulted permutation will be also a solution.
Okay, yeah, this is your observation. This is one good observation. See, if you just say it like this, then this is correct. Take 1 to n and swap any two consecutive numbers, then this satisfies. So this produces a number of examples for you. Let's write this. So this is one observation which kind of falls in line with, do we see a structure in these permutations? This is some sort of, loosely speaking, a structure. But this doesn't mean you can continue to do this, right? So what you are saying is basically 1 to, for example, come to k minus 1 and then swap k and k plus 1 and then continue with normal, right? Just these two are swapped. This permutation, if you take this as a1, a2, an, this satisfies. Yeah, satisfies. But if you keep swapping, then it will not work. For example, if you say now these two are consecutive, k and k plus 2, if I swap them, well, they are consecutive here in the permutation, but they're not consecutive numbers, so it will be a problem. Something like this. So let's quickly verify this observation. What we need to verify is the inequalities. Obviously, the inequalities in this part clearly hold because the numbers are actually increasing. And they are multiple. So 1 times 1, 2 times 2, 3 times 3, k minus 1 times k minus 1. And now we have k plus 1 times k. So let's just write these inequalities like 1 times 1 is less than 2 times 2. K minus 1 times k. Sorry, k minus 1 times k minus 1. And then k times k plus 1 because of the swap. And this is also k plus 1 times k. So these are equal, which is fine because we are saying less than or equal to. And then again, it's getting bigger and bigger. So this satisfies. This is the explanation. But how about if I swap this again? So k plus 2 and k. Look, k plus 2 would come here and k would come here. So this would be k plus 1 times k plus 2, and this would be k plus 2 times k times k plus 2. So it would not be correct. I cannot keep swapping like this. If I have swapped these two numbers, then I cannot swap these two numbers. There is some limit, but this swap idea is good. You know how to construct these permutations by swapping things. What level of freedom do we have? All right, other people, Abdullah and Karim, have you calculated the numbers as a sequence in n and seen a pattern, or have you seen some
Yeah,
pattern?
they seem to be Fibonacci numbers.
Oh, so you calculated some of the numbers and it looks like it's the Fibonacci sequence. Okay. Up to what number have you calculated?
4.
Up to 4, so it's just 1. So you have 1, 2, 3, and 5. Have you calculated n equals 5?
No.
Okay, if you calculate n equals 5, then you can
I calculate in general and it's Fibonacci numbers too.
so you calculated up to what?
In general.
Are you proved?
Yeah, but I didn't write any.
Sorry, I didn't understand. You solved the problem yet, or in how
Yeah,
did you? Ah, okay. Then you should also send your solution on on WhatsApp, and then since it's 2 people who solve the problem, I should write the next problem on the next page. Page. Okay. Thank God, Alhamdulillah, I prepared for this problem while you were working on the other one. So, and one from the same shortlist. We can do another. But please, before starting to work on this problem, write your solutions, both Adham and Karim. Write your solutions and send to me. Do you have my WhatsApp number? Probably no, right? I should.
Yeah, I
Yeah,
don't think so.
yeah. So I should send to you in chat. And others, Abdullah and Kerem, you should still you should continue the combinatorics problem. Shortlist and well, given K. Show that there exist prime P and numbers. There exist prime P and distinct numbers. From 1 to e minus 1, which satisfy, or for which P divides AI plus 1, AI plus 2, AI plus 3 minus I. Or all. Yeah, for now I'm just writing the problem. So the things, are you able to change pages on the whiteboard yourself? Or no? Or when I'm here, doesn't mean everyone is here.
Yeah, I can change.
Okay. So you can look at the other problem, all right. Okay, so let's write this second observation, Fibonacci observation. For n equals 1, the only permutation is, of course, this. So the answer is 1. For n equals 2, the permutations are 1, 2, and 2, 1. They both satisfy. And the answer is 2. This is trivial. For n equals 3, of the permutations, let's see which ones satisfy, which ones don't. Okay. let's see. So these are, we said these are the ones that satisfy. Should make it like this, right? So this one clearly satisfies this. So 1 times 1. See, this fits this structure. This one, this one obviously satisfies. Just nothing has been swapped. 1 to dot n always satisfies, and this is obtained by 1 swap, as Kerem said, and this is obtained by 1 swap. So in this one, 2 and 3 are swapped, and this is 2 and this 1 and 2 are swapped. So these are also good. We can check it ourselves, right? 1 times 1, 2 times 3, 3 times 2. This is 1 times 2, 2 times 1, they are equal, and this is 3 times 3. The inequality holds. But if you look at this one, it fails here. 2 times 3 is not less than or equal to 3 times 1. So this fails. In this one, it fails in the first step. 1 times 3 is not less than 2 times 1. Let me write this better. Write this bigger. 2 times. This is bigger than 3 times 1. Unfortunately, anyway. Okay, 1 times 3 is bigger than 2 times 1. And in this one, where does it fail? Do you see? Who will tell me? 1 times 3, 2 times 2, this is good. But 2 times 2 is more than 3 times 1. So the answer is 3. Now, for n equals 4, it's going to get more difficult. But we should not write all the 24 permutations. We should have an idea to cross them out. So Abdullah, can you help me quickly do this?
You mean how to get them quickly, or?
Yeah, how do you get exactly which permutations satisfy and that the others don't satisfy? How do you convince that the others don't satisfy?
The last two elements are n and n minus 1, or in any order.
In general,
Yeah, for
or
like n
or for n equals 4. So
no,
I mean, is it a conjecture or is this something you have proven? But see, this is a very good thing. So you are basically making an observation of this kind. You are making an observation about the permutation itself. You are discovering a hidden structure, which is not here. You are discovering a structure telling me that the last number must be either n or n minus 1. And the last two numbers must be, you are saying n and n minus 1. Right? Well, let's, this is not exactly correct, I guess, because here the last two numbers are 3 and 1, not 3 and 2. But the last number is, if you say last number is n or n minus 1, that's maybe more correct.
yeah.
But let's see. Let's write the answers, the correct answers for n equals 4, and then let's see what is the observation exactly. What are the correct permutations for n equals 4, and how do we verify this quickly?
We have 1, 2, 3, 4.
Yeah.
1, 2, 4, 3.
Yeah, there are these ones that Kerem has generated. So we can also swap these two, right?
Yeah.
1, 3, 2, 4, and 2, 1, 3, 4. Okay. What else?
We also have wait, just a sec.
And the question is, how do I quickly calculate that the other 19 permutations don't work? Without actually trying 19 of them. Have you tried all 19 of them?
No, I like so the first element is either 1 or 2, and the last one is either n or n minus 1.
Yeah, so how did you verify this? How do you know that this is the case?
Well, it's
Because if you
like well, by the inequality, it's there's gonna be like if we don't do this, we have to like it's gonna fail other elements.
Okay, clearly you have a right intuition, but you have to express it formally correctly. And if you can express it, it will be part of the proof. It will be part of the full solution. So you are walking toward the full solution, so you should be confident about how to say it exactly. So you are saying if the first element is not, sorry, what did you say? The first element is either 1 or 2, right? So you're saying if
Yeah.
the first element is 3, for example, there is definitely gonna be some.
Yeah, because wherever we place 1, if it
Yeah.
it's gonna it's not gonna validate the inequality.
So which inequality will fail? So if I place 1,
In any place other than the 2 first places.
okay, yeah, this is a very precise observation now. Good. So I can write this as so I am leaving this. I will come back to it. So let's write this as observation 3. So if you are saying if AK, so the precise expression is 1. If AK equals 1
And K
for
is
K
equal
greater
to
than or equal to 3,
Oh,
there is a contradiction.
yeah.
What is the contradiction?
We can suppose AK equals 1 and try the
Yeah.
inequality.
Yeah, which one will fail exactly? Supposedly the one
K
with this.
K minus 1.
Oh, okay, great. So K minus 1 times A K minus 1 is less than or equal to K times 1 will be a contradiction,
Yeah.
right? Because this will mean a K minus 1 is less than or equal to K over K minus 1, which is since K is greater than or equal to 3, this is less than or equal to 3 over 2. But then since this is an integer, this has to be 1, but it is not 1, right? 1 is already here. Yeah. So AK minus 1 is an integer. Let's write it like this. Contradiction because contradiction. This is a notation for contradiction because this AK minus, so you have to say this precisely, right? AK minus 1 is an integer and it is different from 1. It is from here. Since, yeah. Normally we know any element in this permutation is between 1 to n, but AK is already 1, so it's gone. So the remaining things are this. The smallest thing here is 2, it's greater than this. Or alternatively, you can just say this is greater than or equal to 2, and you can put 2 here. Okay, but this has proven that 1 is, so consequently, A1 is 1 or A2 is 1. But if A2 is 1, do you have any information about A1?
Yeah, it has to be 2.
Yeah, because you can put this, yeah, in this case, 1 times A1 less than or equal to 2 times A2, which is 1. So A1 is less than or equal to 2. This gives A1 equals 2. So there are 2 possible ways to start. So any permutation either starts as 1 and then something, or it starts as 2, 1. So there is a swap in the beginning and something. So there is either a swap in the beginning and then we don't know what happens, or there is no swap in the beginning and this remains. But definitely nothing from far away comes to here. This is a powerful observation. So you can do the same thing for the last part.
Yeah,
For
the last element has to be either n or like this n-1, and the one before it has to be n.
yeah, let's see. So this is observation 3a. And let's do observation 3b for the last element. So like this. So what is your precise formulation? If you were writing the solution in an exam, you should write it like this, right? So if
So if
something
AK
something there's
equals n,
if what?
AK
Yeah. Equals n.
then either k equals n
Yeah.
or k equals n-1 and an equals n-1.
Okay. So first, let's say k is either n or n-1. And then in the case k equals n-1, you will be able to say an equals n-1.
Yeah.
But first say this. So like this structure, for if this is the case for k less than or equal to n-2, then there's a contradiction. Okay, where is the contradiction? So it should be similar to this.
Yeah, except we look at the element after it.
Yeah, we should look at the element after. Because that's the natural thing. So k times n less than or equal to k plus 1 times a k plus 1. Okay. This doesn't immediately give a contradiction, because if ak plus 1 is big, this would hold. I mean, if this is n-1, for example, if you put it, it would satisfy. However, there is more inequalities you can look at, of course. This is not the only inequality.
Yeah.
So what are some of the other inequalities you can look?
Yeah. So we can just look at all the elements after K.
Yeah.
And we won't be able to satisfy all of the inequalities.
You see, this is a powerful idea. This is a stronger idea than this. Instead of just looking at one inequality, you look at all of them. By all of them, you mean compare all of them to K times N, right?
Yeah.
You look at all of these inequalities. Okay, then. Okay, tell me what do you get exactly?
So we
What
get
combination?
that the all the elements have to be greater than K.
Okay, so you're proving that from such an inequality. So let's try to do this in general, right? By general. So I mean, you are trying to prove that each of these is greater than K.
Yeah.
Yeah, because if you put K, it will not satisfy because this is less than N, right? Except the last term. So this would, so for these, except the last one, you can say,
Yeah.
well, except the last one, here is what you can say. So you have to be precise in this, right? This is less than or equal to, yeah, let's just write I times AI, where I is what? Less than N.
Yeah.
This is less than N, so N times AI. So AI is strictly greater than K for I between K plus 1 and N minus 1. So these elements are above yeah, K plus 1 and above. How about the last one? So wait for me a few minutes. I will need to bring the charger of my computer. So by the way, there is this that we didn't complete. the permutations in n equals 4. So how about Kerem? Have you thought anything further in either direction about these observations, or the calculation of n equals 4 or n equals 5, or along the lines of your own observation? Any of these?
Actually, I'm trying, but I didn't get any observation.
Okay, that's fine. That's completely fine. Because in the exam you have more time to solve such problems, right?
So for k equals n, this also holds. We have that a of n is greater than k.
How did you prove?
So we have n times a of n is greater than or equal to n minus 1 times a of n minus 1. And we have a of n
Okay.
minus 1 is greater than or equal to
Yeah.
it's greater than or equal to k plus 1. Because it's greater than k.
Okay. So you are not looking at this one. Yeah, so let's write it precisely what you're looking at is. So here we looked up to these.
Yeah.
And then after,
And
so
we used
this is what we obtained. And secondly, we look at, you see there is, so this is one idea. And the second one is what you said is
and
we
we
look
use
at n minus 1, a n minus 1 less than or equal to n a n.
yeah.
And this has already been proven. So here, this is very important. Look, k is less than or equal to, here actually we are using k less than or equal to n minus 2. In this one, we have not used k less than or equal to n minus 2. Because even for k equals n minus 1, we would, I mean, this would be an empty set. So yeah, here we wrote the inequalities from k plus 1 to n minus 1. If k equals n minus 1, we would have a conclusion for nothing, but it would not be wrong. And it would not be a contradiction. Even when you have you have a conclusion which is what is called a vacuous conclusion for the empty set, it is still correct and it cannot give you a contradiction by itself. But for k less than or equal to n minus 2, now you can use this and combine this with the previous one, because n minus 1 is here, because it is greater than or equal to k plus 1. With this, now this cannot be equal to k, right? Maybe we should expand this. Yeah, this is what, nk plus n minus k minus 1. So this is greater. See, this is strictly positive. This is greater than n times k. So this shows an is also greater than k. Well, but this observation was much bigger, much more involved than this one. So I will call this observation 4, in fact. It's not of the same kind. It's not as easy. The observation about the first element, I mean, the beginning of the permutation is a much easier observation. Now this one is a more advanced observation. With this more advanced observation, you can certainly complete the problem more easily. But I want to also show you the other ways. Maybe just looking at this and not just looking at this observation, but proceeding in a different direction, improving this kind of observation in a further direction. How can we reach the solution? So there are multiple ways. I want to discuss a couple of them. So from observation 4, so let's wait for a few minutes, for 5 or 10 minutes. Because, well, Adham has sent me a solution, but okay. Karim also sent. I should read. So I want Abdullah and Kerem from you as well. So now I give you, as I said, about 10 minutes. Try to complete the solution from these observations and write it. Writing the solutions properly is really part of the training. It's very important.
But actually here, have we concluded that a sub k, I didn't understand it. Did we conclude that that a sub n is either n or n minus 1?
Oh yeah, you are right. We have not yet concluded because we just obtained a bunch of inequalities. It says that all of these numbers, so all we have done is this. So in the permutation, so we said A1, A2, so somewhere if we have n, then all of these numbers are greater than or equal to k plus 1. Well, these are the indices. If you look at the indices, these are the indices that are k plus 1 and above. And if all the numbers are here, k
But
plus 1
why?
and above, it just must be a permutation within itself.
Why all these numbers are bigger than or equal to k plus 1?
So this inequality and this inequality. For when I is any entry except the last one. So when I is from k plus 1 up to n minus 1, we can write the inequality like this: I times ai greater than or equal to k times ak, which is n. So this gives, well, since I is less than n, ai is greater than k. And for the last entry, you can compare with the previous one. N times an is at least n minus 1 times an minus 1, but the previous entry itself is at least k plus 1. So if you write this, you see this is greater than n times k. This product is greater than n times k. So an, the last entry, must also be greater than k. But notice this thing holds for so this is the final observation. All of these are greater than or equal to k plus 1.
They are greater than or equal to k, but how could we conclude that they are? Oh, okay.
Here, k less than or equal to n minus 2 is crucial because it is not correct for k equals n minus 1. So if k equals n minus 1, so if there is only one, if there is only the last element that remains here, you cannot say that the last element is greater than or equal to n. We do not have anything like this, because for the last element, our proof depends on this, where, yeah, here you see we use strict positivity of this. Here we use sometimes really crucial piece of information used in a small point. But then the contradiction, what is the contradiction here? After all of these numbers are greater than or equal to k plus 1. This number is also greater than, of course, k plus 1. So we have more numbers that are available that are greater than k plus 1. How many numbers are greater than k plus, how many numbers are greater than or above k plus 1? N minus k numbers. And we already have n minus k things here. But we have also this one. Right? So n minus k terms greater than n minus k terms. There are n minus k terms here. But there are. So if you don't count n, you cannot have n again. But the numbers from k plus 1 to n minus 1 has only n minus k minus 1 numbers. This is the contradiction. So does this explain it, Kerem?
Actually, I didn't got it, the last thing, but I think we can say that we have after k n minus k elements,
Yeah.
right?
Yes.
N minus k elements, and all of them must be bigger than or equal to k plus 1.
Yes.
And there are n minus k integers that are greater than or equal to k plus 1,
Yes.
and so n must be among them.
Yes.
And so we have a sub I equal n for some I bigger than k, which is a
Yes.
contradiction.
Yeah, you can say the contradiction like this as well. That's perfectly valid way. Another way to say the contradiction. Yeah, you can say there are n minus k terms here, and there are n minus k numbers that are greater than or equal to k plus 1. So all of them must appear here exactly once, including n. N must also be here, but that's a contradiction. It's just the same way. I mean the same thing expressed with a different logic here. But you are convinced about the inequalities themselves? This and this?
Yes.
Yeah. So, okay, this is a very strong observation. So, see, Abdullah, you had not proven this, right? Before we started writing this down. You had not proven, you had not gone through this.
Yeah.
But you had the intuition. You had made the observation. So what you had to do at that stage? At that stage, the step forward that you had to take is to just confidently formulate the observation, which is as we did here, and try to prove it rigorously. The first step is to formulate the observation. You had something like, okay, the last element should be n or n minus 1 and n cannot be far from the last side. You said these things. But what was an exact formulation of this? When I pressed you to say it exactly, finally you formulate it. And once you formulate it, it's clear that we have to look at the inequalities and try to find the contradiction. And we looked at the inequalities, we saw something has come out, but then the last term didn't come, and for the last term we did something else. So once you get on the track, you progress. The first stage is really to formulate your observation. Similarly, for you, Kerem, for example, you had an observation about swaps. What you needed to do is to make it precise, but this is a semi-observation, so we should continue along these lines. we can make a big observation from this as well, and maybe we can find something along these lines. So we can reach the solution in different ways. Still, we have not completed the solution. So I want everyone to write the solution at the end and send.
I think we can do the rest by induction, right?
Yeah, the rest from observation 4?
Yes,
Yes. Yeah, like what?
by induction.
Yeah, you're doing induction on N, and what's the conclusion of your induction? What's your induction hypothesis statement?
I mean by strong induction, because we assume for n-1 and
Yeah.
and
No,
then
I'm saying the statement you are proving is the number of permutations is
the Fibonacci number.
yeah. And yeah, so far, okay, we've just written this in the form of observations, and we should now, okay, maybe it is better if I just write it neatly as a solution, right, rather than, because it's now close to it. But let's okay, let's just write this as a solution neatly. Oops. And then pass to the number theory problem after this. Okay, solution 1, let's say, because it will be based on our observation 4. I don't need to write the observation 4 again. Based on this observation, what we know is an equals n, or an minus 1 equals n. And in this case, n times, well, n minus 1 times n minus 1 times an minus 1, right? This is less than or equal to n times an. So an is greater than or equal to n minus 1. So an is actually n minus 1. So this shows that that the permutation, end of the permutation, so either the end is n, or the end is n minus 1. Yeah, now the next observation to do here is that now these numbers actually are irrelevant to the rest, because this will definitely satisfy the inequalities with the other. So there is a permutation here already. So here what remains is a permutation of n minus 1. And this is the same thing, just reduced to same pattern in n, reduced to n minus 1. This is the permutation of the numbers 1 through n minus 1, and they have to satisfy the same inequalities, except the last term, and the last inequality is automatically satisfied. And here there's a permutation of and minus 2. And similarly, they have to satisfy the same inequalities. And then these, the inequalities with the others would be automatically satisfied, because here, I mean, okay, we have to justify this. We have to justify this, right? Let's write this precisely. The conditions here are what happened? Yeah. Conditions here are n minus 1, n minus 1. And then the last thing is n times n. This is automatically satisfied. This is obvious anyway, because the maximum this can be is n minus 1, n minus 1. So it really comes to itself. So similarly here, 1 times a1, 2 times a2 less than or equal to n minus 2, an minus 2. This is less than or equal to n times n minus 1 and n times n minus 1, which is the same thing. Yeah, but the thing is, this is also satisfied. If you don't explain this, it will be a gap in the solution. N minus 1, n minus 2, this is less than or equal to n minus 2 squared, which is less than n minus 1. Why do we need to explain this? Because we need to explain that the only condition that remains for this part is these conditions. We have these conditions, so we need to explain that right now we see we have a permutation of the numbers from 1 through n minus 2. But we want to say that the condition on this permutation is exactly the same as the condition that we begin with. Namely, we have these conditions, yes, but we have to show that we don't have any other condition coming from the other inequalities. We don't have any other condition because they are already satisfied. This thing is important, because if we had extra conditions coming from here, that would reduce the number of permutations. So therefore, you can say, yeah, so the answer for n equals answer for n minus 1 plus answer for n minus 2. So the answer is Fibonacci. So, okay, so here we really didn't need the n equals 4 observation. But with n equals 4, if you had made the calculation, 5 and 8, somehow, for example, anyway, somehow with small observations, you could have small observations, you could have convinced yourselves that this is a Fibonacci sequence. This observation 3 also we have not used that as it is. Because observation 4 was strong enough. And with observation 4, we directly calculated the number. So if we compare this, compare what we have reached at the end to what we began with, as I said in the beginning, we started with two thoughts. We said we want to count the number of permutations, but further we want to really understand the permutations better, understand the structure of the permutations. So with the number, with small trials, we kind of convinced ourselves that this should be the Fibonacci sequence. But when we investigated the permutation, we found some observations about the structure, so that there are these three structural permutations, structural observations. So there is this one, but especially this one, which then led us to count. With this structural observation, we became able to directly count the number of permutations with the induction argument. But we can still do more. Even though the problem is finished, we can still use this structural information to obtain further structural information before counting. Okay. This is also an interesting thing to really exhaust the problem. In the meantime, I will try to rearrange the things in the board. Let me see how I can do this. So I want to say this again because I may not have expressed myself clearly, right? So really, how do I take this and move? To explain this better, select. Okay, this one I will call observation 0 because this is just about the counting of the small values. Now these are the, so I will change the numbers of the observations. This is, I will call it 2 and this 3. The solution is based on observation 3. Now I will explain what I mean. Okay, as I said, just to repeat myself, we had a problem of counting certain permutations. Permutations had a condition, and we wanted to. So on the one hand, as I said, we looked at the number of permutations for small numbers and observed the pattern, convinced ourselves that Fibonacci could be the answer. But this doesn't. This is just a motivation. But on the other hand, what really progresses us toward the solution is before counting, investigate the permutations themselves. Try to understand the structure of the permutations. And when it comes to this, there was this small observation of Kerem about swaps. Now there was this observation about the location of 1, which kind of indicated something about swaps. And then finally there was this observation about the location of n, which was a bigger observation. It also indicated something about the swaps, but this was much stronger structure. This directly led us to the solution, because with this structure, now we are able to count by induction. Okay, so we found a little bit of structure, So we answered this question a little bit. Do we see a structure? Yes, we see a little bit of structure. And with this much structure, we found the answer. Okay? We found the answer, the number of permutations. But now we can also ask the question, can we even see more structure in a way that convinces us? Not just the number, but for example here, the structure that we see is about the end part only. Can we even say something further down? In fact, the answer to this is also induction. Because we can, we have found a structure about the end part of the permutation. And after the end part, we have noticed that the remaining part is just the reduced problem, the same problem reduced. We use this reduction observation in our induction argument for counting. But we can also use the same reduction observation in an induction argument for, not for counting, but further investigating the structure of the permutation. So for example, I can apply the same idea to this permutation. So the last term must be n minus 1, or the last two must be n minus 1 and minus 2. Something like this. So, or similarly, I can say the last term must be n minus 2, or the last two terms must be n minus 2 and minus 3. If I follow this line, what do I see? So I want you to think about this. This kind of thoughts are important to in order to grasp the more general abstract mechanism of combinatorics in general. Sometimes they give us counting problems and we are satisfied when we can count. But how do we become able to count? Okay, we find some information, some hidden information. But maybe we can find even more hidden information for fun, or for other purposes, for other ways of counting as well. So this is why I want you to think about the problem a little bit further. Is it now? Am I clear? Is it clear what I'm asking you to do, or not yet?
I think so.
Yeah. How about the other guys? Adham, Karim, Karam?
Yeah, it's clear.
It's clear, right? So you will basically apply this steps all the way to the end, and it should be sort of summarized. You should sort of summarize this as one information. Because with this, it depends on, it looks like, there are lots of cases. This can branch into 2 cases, and then each one can branch into 2 cases. There are lots of cases. But instead of these cases, what the pattern that emerges at the end should be summarized as one thing. And then once we summarize, once we formulate it, again, it will come from intuition. But for this also, I recommend you to do small cases. Like n equals 6, n equals 7. Now it is doable. In the beginning of the problem, even n equals 4 was big. Even n equals 4 would take time. But now n equals 6, n equals 7, and even n equals 8 is doable. Let me even try to do it with you. We want to investigate the structure of the permutation. Permutations further by using observation 3. Yeah, like in the solution, by using this observation 3. like in the solution. I mean, observation 3 and the reduction of and reduction to n minus 1 and minus 2, exactly like in the solution. Okay, when we write it like this, we know what we want to do. Let's check some more cases. Let's start with n equals 4 that we had not done. So the last term could be 4. If the last term is 4, then there are already 3 answers here. We know 3. If the last thing is 3, we have 1, 2, or 2, 1. But if the last thing is not 3, but it is like this, then this is what can happen. Or alternatively, if the last 2 terms are 3, 4, then the remaining things can be 1, 2, or 2, 1. So these are the 4 permutations. Sorry, 5 permutations in the case of n equals 4. For n equals 5, when the last term is 5, we should have these 5 permutations. So all of these with the last term added 5. Yeah, okay, let's write it exactly like that. Let's write everything. Alternatively, if the last terms are like this, then we should have permutations of 3 coming here. For n equals 6, we should have all these permutations with 6 added at the end. So 1, 2, 3, 4, 5, 6. 2, 1, 3, 4, 5, 6. 1, 3, 2, 4, 5, 6. Then what does this say? 1, 2, 4, 3, 5, 6. And this one says 2, 1, 4, 3, 5, 6. And this one says 1, 2, 3, 5, 4, 6. 1, 3, 2, 5, 4, 6. 2, 1, 3, 5, 4, 6. And now, what more? The last parts can be like this, 6, 5, and then we should use these. 1, 2, 3, 4, 6, 5. 2, 1, 3, 4, 6, 5. Yeah, that's better. 1, 2, 3, 4, 6, 5, right? 2, 1, 3, 4, 6, 5. 1, 3, 2, 4, 6, 5. 1, 2, 4, 3, 6, 5. 2, 1, 4, 3, 6, 5. So these are the 13 permutations. Look at them. Do you see any pattern?
Yeah, they're just previous permutations with a suffix either n minus 1 n or just n.
Yeah, that's right. But this is a recursive description. Without recursion, just directly at the level of n, these permutations. So what's a characteristic of these permutations? I mean, we obtained them, as you said. We obtained them by looking at the previous permutations and did this. But this information has to be summarized. Has to be summarized without recursion, because when you refer to it, it becomes, you know, sort of n steps like that.
So can we say that each element, say 3, is either in the it's either in position 2, 3, or 4 for for any k. It's either in the k minus 1th, the k plus 1th position.
Yeah, this is correct. Great. Every elements cannot move too much. It either stays or moves one place right or one place left. Yeah, but then it's sort of basically what you are saying here is the endpoint case of this. The element n can either stay or move left, but when it moves left, the left term automatically moves right.
Yeah, but
So we
it's
should
true
also
for,
say this somehow.
isn't this true for all positions?
Yeah, all positions. So what is the statement exactly? If k is in position k, okay, that's fine. If k is in position k minus 1,
then k minus 1 is in position k.
yeah, then k minus 1 is in position k. So what is, yeah, this exactly says that k and k minus 1 are swapped.
Yeah.
So how would we formulate this again? So what you have just said, if k is in k, we don't say anything. If an element is already in its position, we don't say anything. But for the elements that are not in their position,
They're swapped once.
What?
They got swapped once, basically.
Yeah, only there are swaps of consecutive elements, and there is nothing else. It's just there are swaps of consecutive elements, and other than this, there is no other motion. Now, once it is swapped, they cannot move again. So let's look at the swap. So this was the original swap observation that Kerem had said. But now, if we look at the swaps in the answers, yeah, what do we see? So here there is no swap. Here, this is the swap. So 1 and 2 have swapped. Other elements remain, right? Here is the swap. In this permutation, here is the swap. In this permutation, this one and this one are the two swaps. So, yeah, what is different from in this permutation from what Kerem has said is that if we swap k and k plus 1, we can also swap l and l plus 1 in a different place. And we can swap, you know, z and z plus 1 in a different place, as long as they don't interfere with each other. But once you swap, for example, 3 and 2 like this, now you cannot swap 2 and 4. They are not consecutive anymore. You can only swap consecutive integers in blocks. So you basically have blocks of 2 which do not overlap. You have domino tiling kind of thing, which do not overlap, adjacent pairs which do not overlap, and you swap them independently. Here there is no swap. Here is the swap. Here is the swap. Here is the swap. Here these are the swaps. Here this is the swap. This is the swap. This is the swap. So 2 swaps. Here these are the 2 swaps. And here there is no swap. Here, this is the only swap. This is the only swap. This is the only swap. These 2 are the swaps. This is the swap. These 2 are the swaps. These two are the swaps. Now this one is the swap here. And this and this are the swaps. This and these are the swaps. This and these are the swaps. And now there are 3 swaps here. In these permutations, okay, this is our observation that all the permutations which satisfy the condition must be like this. How about conversely, can we also say that when we just swap like this, it satisfies? Well, yes, we can say it. It will basically be like this observation because it will be obvious. I mean, here we have explained that we can swap 2 numbers. And it's kind of clear that we can also independently swap 2 other numbers here, as long as they don't touch each other. So we can explain the converse part easily. The forward part is that every permutation here must be like this, is a statement by itself. So how do we prove this statement? Now this has been our observation by looking at the small cases. Our goal was to investigate the structure of the permutations further by using this observation and the reduction argument, and indeed we looked at the small cases using observation 3 and the reduction argument. And from this, we made a new observation about the structure of these permutations. Now we want to prove it. Here is our claim. Claim the permutations in question are exactly those obtained as how do we say, obtained by swapping several, well, obtained by swapping several non-intersecting, non-overlapping, okay, yeah, non-intersecting consecutive pairs. So we are talking about consecutive pairs, but non-intersecting consecutive pairs. It's not like 3, 4, and 4, 5. These are intersecting consecutive pairs. So several non-intersecting consecutive pairs, we swap them. And this way, we obtain permutations, and these are exactly these ones. So in other words, we can say we have indices I1, I1, I2, let's say IL, with difference between them at least 2, so that, for example, this index and this index, the next swap indices with, say, yeah, let me actually write it better. We have indices. Look, instead of saying that the difference is 2, it is better to write it like it's I1 less than, obviously, I1 plus 1, and this is less than I2, I2 plus 1. Yeah, we have such indices. I3 plus 1, strictly less than IL plus 1. We have such indices such that what? In our permutation, Aij equals what? A of Ij equals Is it understandable what in this index pairs I am talking about?
So we just formulated what we said.
Yeah, we are just mathematically formulating what we. So here is the verbally complete statement. So I am saying, in other words, this is the mathematical way of writing it.
Yeah.
So in the mathematical way of writing it, I should say Aij equals. Sorry, this is not L plus 1, IL plus 1. Yeah.
What do you mean Aij?
Yeah, so this is a good question. So what I mean by these indices I1, I2 is this. The indices that will be swapped. So for example, here 2, 1 and 3, 4 are swapped. So this is 1, this is 2, this is 3, this is 4. For this example, 1, 2, and 4, 5 are swapped, right? So 1, 2, 4, 5. The numbers that are swapped are like this: 1, 2, 4, 5. So I want to say A1 is 2, A2 is 1, A4 is 5, A5 is 4.
Ah, I see.
So in this case, 3, 2, 5, 6, for example. 3, 2, 5, 6 are the things. And for the other indices that are not in this list, AK equals K.
So Aij is equal to um I either Ij plus 1 or Ij minus 1.
No, it's IJ plus 1 only. There is no IJ minus 1 because they already come like this.
Ah, okay, yeah.
And AIJ plus 1 equals IJ.
Yeah.
Maybe we can say it better like this: AK equals, if K equals IJ, then AK equals K plus 1. If K equals IJ plus 1, then AK equals K minus 1, which is IJ. So this is IJ plus 1. This is IJ. Otherwise, AK equals K. So this is a claim. Now we have to prove it. But the proof will be essentially the same thing. How did we obtain the claim? By using observation 3 and the reduction argument. So the proof should be exactly like that. We have to prove this claim exactly in this manner. It should be exactly like the solution. Proof of the claim. Again, based on observation 3, we already know this. This or this. And here we explained above that this is a permutation of n minus 1, and the only condition on this is exactly our conditions, and the only condition on this is exactly our conditions. So we can prove the claim by induction. Right? We can prove the claim by induction. The claim is correct for n equals 1, obviously. There is nothing to swap. For n equals 1, the claim is obvious. So we have to write it like this. In fact, even here I should have said, yeah, here we didn't need to say induction. Here we didn't need to say induction. We just did the recursive formula. But here we have since in this case it's just a formula, just numbers, we don't really say it as induction. Just the recursive formula, and the recursion is solved. Because the recursion, so here to really complete the Fibonacci, we just say answer 1 equals 1, answer 2 equals 2. So automatically it gives Fibonacci from the recursion. But in this case, we have to be careful with the induction. We prove by induction. Hassan, you have joined? Great. Great to see you. You have joined. I was just looking at the solution that you sent, but I will be able to read it later. Okay, it's fine. Okay, I saw in chat that you say your mic is broken. That's fine, but your speaker works, so you hear us, right? We prove by induction. For n equals 1, it's obvious. Nothing to swap. So nothing to swap means L equals 0. Right. So these are the permutations that satisfy this. And in general, for n, for any n greater than or equal to 2, we have that the permutation satisfies this. The last part is n, or n minus 1. We know this by observation 3 and the reduction argument. So we should, and so this is a permutation of n minus 1 with the same conditions. Permutation of n minus 2 with the same conditions. Therefore, so right now we are proving the forward statement in the claim, because this is an if and only if claim, right? We are saying if the inequalities are satisfied, then the permutation is obtained by swapping several non-intersecting consecutive pairs. And conversely, if it is obtained like this, then the inequalities are satisfied. Yeah, we should even say this in the beginning, right? Proof of the claim. Proof of the claim. So from the inequalities, so I will call this statement the mathematical formulation here, the swapping thing, is the structure condition. So there are two things to prove. From the inequalities implies the structure. This is one thing to prove. And the other thing is structure implies the inequalities. Structure implies the inequalities. Yeah. Anyway, for inequalities implies the structure, it is like it will be this induction thing, right? Because from the inequalities, we know this. This is our observation 3 coming from the inequalities. And this is our reduction argument. And we see that this part satisfies its own inequalities. So in this part, it has to be just, you know, several non-intersecting consecutive pairs that are swapped. So it will just be so in this case, the swaps will be, in this case, there will be some pairs swapped, some pairs swapped, and the last one is not in the swaps, right? In this one, it's like this. So there are swaps inside here. The last one is not in the swaps. But for this one, what we basically see is there are swaps. Swaps, and including the last two is also swapped. The last two and n minus 1 also swapped. You see, is this a proof? Yeah, I guess this is a proof. I mean, just a visual way of writing it. But to be mathematically precise, we can do it with this. Because this is the structure condition, we can actually do it with this. So we can say, by induction, there exists I1, I2, IL, okay, which satisfy this. By induction, I1, I2, IL exist. It satisfies this. Now, by induction, this formula holds for all k from 1 through n minus 1, and it also holds for k equals n, clearly by, as we see here, an equals n. And in this case, we can say by induction again, I1, I2, IL exists. Now I will define IL plus 1 as n minus 1, and this formula will hold for all k from 1 through n minus 2, and it will also hold for k equals n minus 1 and n, because as we see, they are n and n minus 1, and they will hold in this sense because we are defining IL plus 1 as such. So to write it, I mean, more formally, I1, I2, IL exist by induction, and we use the same. Same for n. In this case, I1, I2, IL again exist by induction, and we further define IL plus 1 equals n minus 1, and IL plus 1 equals n, obviously. Because defining an IL is defining a swap. So when you do it like this, to formally prove, of course, that would be how you write it. Now, from the structure to inequalities, just to finish, what would you say? If this satisfies, well, it doesn't have to be very different. It's almost the same argument. Maybe just hidden within the same argument. If we just have swaps like this, then the inequalities are automatically satisfied. Well, it's just in fact what we did here, right? This observation 1 above. Because when we swap them, we see this is what happens. K times k plus 1 and k plus 1 times k. If we swap another one, again, same thing will happen here. But they will not interfere with each other. These numbers are smaller than these numbers. In any case, it will be like that. All right, with this I stop. Well, just one problem took more than 2 hours because it's not just the problem that took so much time. In fact, it didn't take you so much time to solve it. You solved it in maybe, yeah, some of you solved it in less than 1 hour, and with the others together we solved in about just slightly above 1 hour, as I expected. But I gave you this additional discussion because we are trying to, in the training process, we are trying to make the most of our training time. We are trying to utilize the problems as much as we can, because from each problem we learn ideas. We learn structures, the general structure of combinatorics and other areas of Olympiads. We learn structures, and we learn how to get intuition about the problem, how to formulate our intuition, how to express it mathematically, how to formulate and how to prove. We learn these general principles in all the problems in various ways. So when we solve a problem, we don't want to just usually, in the training, we don't want to just pass to the next problem. We want to utilize the problem to the best, what more can I prove about the problem? So this is why I gave you this discussion, which is very useful. So this is why it took more than 2 hours. So with this I can finish, I think, today's lesson. But maybe I should just write, this is basically observation 2. Sorry, observation 1. Observation 1. So now we can make our concluding remarks and finish the lecture. I don't have anything to say, I guess, unless I forgot something. Did I forget anything? Do you want to ask me questions?
Do we send you the solution of the second problem?
Yeah, you can send it. But it would still be nice for me to discuss it. Maybe, I mean, I will choose other problems as well, but yeah, I mean, certainly I will choose, inshallah, other problems for the next lecture. So next lecture I expect to have with you next week, also sometime during the weekday. Most likely Monday. Actually, Monday is the only day that works for me. If it is possible for you, we can have a lecture on Monday, inshallah. And after that, other lectures, we can have other lectures after the Eid. Okay, and after the Eid, I will be, inshallah, more free. I can give you two lectures per week. So if it works out for Monday's lecture, I can bring other problems. So just send me, as you said, Edhem, just send me your solution to the next problem, N1, by WhatsApp. Yeah, if all of you solve it, maybe we will not discuss it. Maybe you solve it in a different way. I will just give a small discussion like this for half an hour about that. But in any case, inshallah, we will do other problems on Monday. Yeah, but send me your solutions. That's definitely important. Yeah, you can type them up, write them up, and send your solutions. That will be helpful. Any question about?
Did you want to share the other problem with everyone? I don't know if you already did, but the other problem, were you going to share it with everyone, or I don't see it here, that's why I'm asking.
You
It's
mean
on
the
page
number
2.
theory problem? The next one?
It's on the other page. Okay.
Yeah, it's on the other page. yeah, we just don't have time today to discuss. Yeah, basically you can treat it as homework, and then send me your solutions. So any other remark, either about the problem itself, our observations, our solutions, or the claim or the proof of that, or generally about our lectures or about IMO? Anything? If not, inshallah, see you.
Thank you.
You're welcome. Inshallah, see you. Thank you, Tahsin, for arranging this and joining again.
Yeah, thanks for the lecture. Sorry, I missed part of it. But,
Yeah,
Sorry.
no, it's okay. I just told them that next week the only day that works for me is Monday.
Okay, yeah, I heard that part.
Yeah, so that if that works for everyone, you can arrange it, and I can send you the link again.
Okay, great. Sounds good.
All right,
Thank you.
thank you. So recording, should I send it to you?
Yeah, send it to me, and then I'll get it posted.
All right.
Okay.
Great.
All right. Thank
See
you.
you.
Bye. Bye, everyone.